Hello and welcome back to part 4 of our chapter 9 series. In 9.6 we're going to talk about power and sample size. So this is where it starts getting maybe a little bit confusing. Up until now, everything we've gone over about null hypothesis, statement of no difference, what's considered a status code versus our alternative hypothesis to the hypothesis we're testing against. Moving on to our test statistic, which for right now is the z-stat we're testing for. We're going to calculate a z-stat and then turn that into a p-value, then take that p-value and turn it into, compare it against the significance level, which is our alpha. So now we're moving into power and sample size. And when we have power and sample size, there's two types of errors that can potentially occur. There's what's called a type 1 error and a type 2 error. A type 1 error is an erroneous rejection of a true null hypothesis. Type 2 error is the retention of a false null hypothesis. So to show this in a little bit more of a chart-like table, here we have our truth and decision and the potential outcomes. So if we have a true null hypothesis and we retain a true null hypothesis, it's the correct retention. However, if we have a true null hypothesis and we reject the null hypothesis, but the null hypothesis is actually true, this is called a type 1 error. So say we do an example like we've been doing where we have, we collect a data set, compare it to our null hypothesis, and we say, oh, our p-value is 0.001, and so we're going to reject the null hypothesis because our information we have states so. Well, and we say that we had an alpha level of 0.05, and we had a p-value of 0.001, so we reject a null hypothesis. Well, on the face value, we are correct. However, we aren't correct, and what we're saying is that could be a type 1 error. When you reject a true null hypothesis, you can have a type 1 error. And a type 1 error is equivalent to, what we're citing is that alpha level, is the probability of having a type 1 error. In simple terms, it just is, the data we collected suggested that it was, we could reject a null hypothesis, but the data we collected wasn't as good as it could have been, and if there's repeated tests done, so you will see that it was in fact incorrect. Just the same on the other side, when we get to a type 2 error. Type 2 error is when we say, oh, the data we collected was, not sufficient enough, and we have to retain the null hypothesis, right? So the data we collected didn't state or show a difference, any difference there, so we retained the null hypothesis, when in fact the actual null hypothesis itself was false. So if the null hypothesis itself was false and we retained it, that is called a type 2 error. Okay, so these are just the two potential errors that you can get when we're doing our hypothesis testing. So alpha is the probability of a type 1 error, and B is the probability of a type 2 error. So our alpha level, when we set it at 0.05, we're saying that we're willing to say there's a 5% chance that the data we're collecting, up to a 5% chance that the data we're collecting could be incorrect. That's what we're saying by an alpha level. And our beta is the probability of a type 2 error. So when we get to power, the traditional hypothesis testing paradigm considers only type 1 errors. However, we should also consider type 2 errors. And beta is the probability of a type 2 error, which is found by 1 minus beta equals power, which is the probability of avoiding a type 2 error. Remember, we don't want type 2 errors, but they can happen. So the way you found it is with power, which is 1 minus beta. So when we do a power of a z-test, and apologize for not all the formulas coming through on this one, but here's our equation. So we have 1 minus our beta. It's going to equal our this little symbol here is called phi. So 1 minus beta equals phi. Phi is equal to z of 1 minus alpha over 2 plus our mu null hypothesis minus our mu of our alternative hypothesis, the absolute value, so these bad boys right here, the absolute value of this value multiplied by the square root of over the standard deviation. Okay, so this is where phi represents the cumulative probability of a standard normal z-score, where phi of 0, so phi of 0 is 0.5, remember? So if you had like a z-score of 0 and you went to the book, you have a cumulative probability of 0.5, 50%. It's the very middle of our chart. Where our null hypothesis, mu, represents the population mean under the null hypothesis. U of A represents the population mean under alternative hypothesis, and the other values you know, sigma, standard deviation, so on and so forth. So calculating power example, so if you had a study of n equals 16 and retains a null hypothesis of mu equaling 170 at alpha level 0.05, two-sided, what is the power of the test conditions to identify a significant difference in the population mean if the population mean was actually 90? So here, remember, we have our 1 minus beta over alpha. I'm not sure why PowerPoint doesn't like these values going through to our mu null and mu alternative over the standard deviation. And when we plug the values in, we're going to have our phi is equal to negative 1.96 plus the quantity of the absolute value of 170 minus 190 times the square root of 16 over 40, which then you'll get phi is equal to 0.04, which if you go to table B and look up 0.04, you get 0.5160 from table B. And that is what your power is going to be for this particular test. So you consider two competing samples, the distribution model. One model assumes that the null is true, top curve, and the other model assumes that the alternative is true. And so this is that illustrated example here. So here's where we have our, where we're getting our alpha over 2, and then our power. So at the same point with our alpha over 2 and our power shown here at 0.5160, assuming the alternative hypothesis is true. You want to strive for a power of at least 80 or higher. The higher the power, the less chance there is making a type 2 error. Reasoning behind power is when alpha 0.05 two-sided will reject the null when the sample mean exceeds 189.6, which is the right tail top curve, and the probability of getting a value greater than 1.96 on the bottom curve is 50.6, 5160 corresponding to the power of the test. And so that is the power formula and reasons why. The following up is the sample size requirements. This is where we're trying to figure out the required sample size for a two-sided z-test to achieve a power given. So we're trying to figure out n here, right? Sample size n. So if we don't know how much sample size is needed, we plug in this equation and we can figure out our n, which once again PowerPoint doesn't like me this week. So we have our standard deviation squared times the quantity of z of 1 minus beta, which is our power, plus z of 1 minus alpha over 2 squared over delta squared, where we have 1 minus beta is desired power of the test, alpha is desired significance level of the test, our standard deviation of the population, and delta as this triangle is the difference between our mu, our null hypothesis and alternative hypothesis means. It's the difference worth detecting. So an illustrated example of this is how large a sample size is needed for a one-sided sample z-test with 90% power and an alpha of 0.05 two-tailed when we have a standard deviation of 40. So the null hypothesis, as we've been using for the males, is 170. The alternative is 190. We look for the difference, which is our delta. So it's 170 minus 190, so it equals negative 20. So our n is going to be, once again, the standard deviation sigma squared times z 1 minus beta plus z 1 minus alpha over 2 squared over the delta squared, which is 40 squared times 1.28 plus 1.96 squared over negative 20 squared, which gives you a value of 41.99. We will round this up to 42 to ensure adequate power. Some people will even round this up higher, based on if they believe, people are going to drop out of the study, they have lost to follow-up. So in order to achieve this, you need at least 42 entries for your data set. So you might want to start with 60 people, because if you have lost to follow-up, dropouts, et cetera, any other reasons why, you're going to lose this. So you never want to just recruit 42, because then if one person drops out, you won't have the adequate power to, you won't have the required sample size to have the adequate power for the particular test you're running. So here's an illustrated example just showing you the power of 90 that they were doing when we have our alpha over 2 for our x bar, assuming our null hypothesis is true. And as you can see, the line going down, moving it over. Here you go. So the sample size required, illustrating increasing the sample size shrinks the standard error. This means the sampling distribution increases the power. So kind of also goes along with the central limit theorem. As you increase the number of participants in a study design, you're going to increase the power, and you're going to get a more accurate representation of the true value of mu. Okay, and that is the end of chapter 9. There is a lot of information, it keeps going, and as I said before, everything's going to keep building on each other, so please stay on top of everything, and if you have any questions, always feel free to contact me.